So we have finished our Kumada reaction. Now we will see the next coupling reaction, which is Suzuki coupling. This involves organoboranes as coupling partners. Here, palladium or the nickel act as catalyst with some additive, generally the bases. So here we have Rx, R dash, B, Y2. This is your organoboron compound. You will be having nickel cat or palladium cat with base and forms RR dash. So we have different groups. If it is Br2, like generally a tri-alkyl borane. If it is BOH2, then it is boronic acid substituted basically. If it is BOR2, then it is boronic ester. And if it is BF3, then it is trifluoro. So different names for coupling partners when we are having different substrates attached with it. So here the additive that we were talking about is basically a base is needed, and bases such as NaOH, NaOMe methoxide, fluoride, which can act as a nucleophile. So when we have RBOH2, when we have a nucleophile over here that attacks onto your boron, giving a negative charge onto this one, and OH2, this actually transfers the charge to the R group, and therefore this is now more reactive carbanion species and reactive for transmethylation. So this is the role of the base and this boron partner. So far we have seen the bond formation between the aryl groups. Let's see the bond formation between two alkynyl centers. So first one that we are taking this is the isomer, and we have this is a boron partner, and the other halide is this one. And this is P partner. You will see here. So these are two different alkenyls, and we are using and lithium OH as base. So what will really happen is this double bond here and this double bond here, this part is going to be as such. Now this is going to be as such. Basically, we were having D here and E here. And this E has been maintained and this D has been maintained. So Z and this E. So both Z and E are retained. So this is the beauty of the Suzuki reaction. So far, if there is any doubt, please let me know. Then we can move ahead. So I hope the two reactions that we have spoken about, Kumada and Suzuki. In Kumada, we are involving organolithium or organomagnesium reagents, which are basically called as Grignard reagents, and palladium is the main catalyst over there. The active species has always been palladium zero because it has to undergo oxidative addition. And in Kumada also, even if you start with any mixture of the isomers like cis or trans, you will always end up getting one major product, exclusive product, whichever is in the majority form. Then we move to the Suzuki reaction where boron are the coupling partners, organoboron compounds are the coupling partners, and there can be nickel catalyst or the palladium catalyst. This involves a base because it has to activate a more reactive R minus the carbonide, which can help in the transmetallation step very quickly. With respect to the different boron substituents, the names are different. And then we saw how the bond is being formed between two alkyl centers and how the geometry has been retained. Like if we are starting with Z and E, it is giving a Z and E confirmation in the product as well. So why Suzuki reaction is seen much better than why Suzuki reaction is better than Hamada. If you will carefully, sorry, if you will carefully see, this involves organoboron compounds, and this involves Grignard reagents, which basically are functional group intolerant. So they cannot actually tolerate a lot of functional groups. Because of that, the Kumada coupling becomes certain restrictive towards certain substrates. So let's see if, for example, the reaction of acidic substrate. So if I'm taking OTF NH CO2R and CO2M. This is basically a group, acidic group, and in presence of boronic acids, palladium PPH3, K2CO3, which is a base, it would give you, this is your leaving group, this will go out, here the AR will form and it would retain whatever it was there earlier. It will form into 74 into 94 percentage. No racemization, and also this group is having functional group tolerance. It has a functional group tolerance, which is not possible with the Kumada. Also, the beauty of Suzuki reaction that it can do a carbonylative coupling, meaning the insertion of carbonyl group and forming a ketone. We are starting with a aryl iodide and sp3br2. This is a carbon which is N-octyl, so this is sp3 group. This is your sp2, and we are treating it with carbon monoxide in presence of palladium PPH34 and K3PO4, which is your base. Now this carbonyl group will get inserted in this one. Generally, we were having a N-octyl directly. Now C double bond O will insert and N-octyl will be here. So this is basically your carbonylative coupling. So this is the comparison with the Suzuki and Kumada. Now we can move to our third category, which is Negishi reaction. The name it is coming when we are using a zinc coupling partner. So when we are having Rx plus R dash zinc X in presence of catalytic amount of palladium 0, it will form RR dash. Now this is a zinc reagent. Since these are having, this is less nucleophilic compared to lithium, R lithium and RMGX. Therefore, it has good functional group tolerance, which is absent in Kumada reaction, right? So also if we use the bulky ligands, then it becomes even more better. There is a limitation that Kumada reaction, it actually fails in. Firstly, we said that it is not having a functional group tolerance. Second, that it also fails in ketone synthesis, where Negishi reaction works. That will work. So basically, if we are starting with an acid chloride and we are treating with zinc chloride butyl, now this group cannot be treated in presence of the Kumada reaction, like the lithium or the magnesium reagents, because they will react, but this will not react as such. So we have the desired ketone as this one. Therefore, Kumada is useful in many ways, but it is having less functional tolerance and it is having and it is not applicable for the ketone synthesis. Moving ahead to our fourth reaction, which is Clay reaction, and this involves tin systems. This involves organotin compounds as coupling partners. The beauty of this reaction is every functional group can be tolerated here. This reaction is mostly performed by academicians, but not very applicable to industries or medicine. Why? Because the R3SNX, this tin is highly toxic in nature. So industries do avoid toxic reagents. However, it still has a lot of applications. If you see RX, R dash, SN butyl 3, palladium 0 as catalyst, and certain additive to form RR dash. Now here, the beauty of this reaction is there R can be aryl, it can be vinyl, it can be alkyl, it can be alkenyl. Similarly, R dash can be aryl, vinyl, or alkyl, so anything. So it would be useful in many, many substrates that do require only the standard conditions, not very harsh reaction conditions. So let's see some examples. We have acid chlorides, that two acid chlorides, and it will react with the SnMe3, SnMe3 in presence of palladium 0 catalyst, THF solvent, and at room temperature. As I mentioned that it works at room temperature conditions. So what it will give you? It will give you double bond. So instead of now this, it will go like this way. We'll count the number 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. And 6. Right? So this is your product, which has been found in 62% yield. Now, another example of instiller reaction is it also undergoes carbonylative coupling, which is not possible with Kumada, but Suzuki can do that. pH, which is phenyl, this is iodide, butyl 3SN. Room temperature reaction with a catalytic amount of palladium, PPH3, 2Cl2, and carbon monoxide, which is the important reagent. So it would retain the geometry and give us the product. Also, now if you want to synthesize aldehyde, ketone is okay. Ketone, we know that it can form, but it can also form an aldehyde. So aldehyde synthesis is also possible if we use it in hydride as a reagent. So we have this furan and we have H. Now instead of any R group, there is hydride. So what it would do, firstly in presence of the catalyst, 45 psi pressure of carbon monoxide, and it would give you, instead of here, firstly it would introduce a C double bond OH, and this is an aldehyde. This can only be possible with a still reaction. So have we ever seen the reaction with alkyl electrophiles as substrate? Meaning that if I have this substrate which is sp3 hybridized and I'm using a coupling partner, I don't know which catalyst would be used, and it should give me a RR dash. But generally what happens, let's see the mechanism. So what really happens is, so this RBr, when it is being treated with palladium 0, which is your active species, it would undergo oxidative addition. So this oxidative addition would break this bond and it would form palladium in plus 2, and this would be like R, and this is Pr. Now at this position, it is having H and H. This is alpha and this is beta. I'll make in another window. So we have made this palladium and Br. Now this center is having H and H. This is alpha center, this is beta. Before it goes to combine with your R dash metal, it actually does beta hydride elimination. So it gives out one of the hydride outside, and therefore it comes in contact palladium. So this turns out to be an olefin product, and there won't be any formation of R and R dash. It will not form so because it undergoes the beta hydride elimination. So solution for this is to avoid beta hydride elimination in alkyl substrates. Bulky ligands have to be used in catalyst. For example, if I have now this and a boron center coupling. Now catalyst I have used as palladium acetate, and my ligand that I'm taking is tricyclohexylphosphine. So this is quite bulky in nature, and in presence of K3PO4, because this is a Suzuki reaction, it would give you the product as sp3 bond formation. So this can work, which is also 80% in yield. So this can easily work out over here. So now we have seen that, okay, we got the solution that alkyl halides can work, or the primary halides can work in this case. So primary halides, the alkyl partners, they can work. So they can undergo. But what about secondary and tertiary? So they can't do any reaction. Why is it so? Because generally we have an oxidative addition step. It's an SN2 mechanism, meaning there would be an inversion of the symmetry. And this kind of thing is not possible. It is not possible with secondary or tertiary alkyl substrates. So firstly, to prove whether it is SN2 or not, what we did, we have a substrate where we have made it a chiral deuterated version, and we treated it with boron precursor in presence of palladium 0 catalyst and PR3 NaOH heating. This is a Suzuki reaction, right? So we are expecting this to be removed and then pH to be coming in the picture. pH came, this is tertiary butyl, and it inverted the center, this one, and giving the product. So this is a major product, and inversion has happened. That means oxide is an SN2 mechanism. This that way only it can work. So this is the scenario. Secondary and tertiary substrates can't be used. So what is the better solution now? For involving tertiary and secondary substrates as well, we need to change the mechanism. Like it should not go via SN2, it should go via radical mechanism. For that, nickel as a catalyst, it would be more prone to react with electrophiles, these electrophile substrates via radical pathway than palladium, which prefers SN2 pathway. So now we need to change the catalyst over there. So in that regard, when we have a 2-degree alkyl halide, and this is an sp3, in presence of the catalyst nickel chloride and a ligand and a base, it would form the product 80%. So this is formation is happening only when we are using a nickel catalyst. And here the ligand is a chiral ligand, NHMe, NHMe. So this is the solution for having your secondary and tertiary to be working in this reaction. Followed by that, we have asymmetric stereo convergent Suzuki reaction. Whatever you use, even if with the racemic mixture you are using, you will end up having only one product as exclusive product. So when I'm using this particular species, where this is a racemic mixture having both R and S forms, and we are treating it with ArBr2 in presence of 8% nickel bromide and ligand and potassium oxide, tertiary butoxide, potassium tertiary butoxide at minus 5 degrees. So what it would form? It would form a exclusive product which is having this stereo nature, which is 90% enantioselective. Selective. So even if you start with racemic, you will end up getting this one. This is called asymmetric stereo convergent Suzuki reaction. What really happens here is, so considering that this whole species is like this way. So we have this R, AR, and R, AR, right? This part I'm talking about. And it would generate a radical because we are taking a nickel catalyst. So it will undergo via radical mechanism pathway. So it is forming R and AR. Now, so 2 degree is more stable radical than 1 degree, that is clear. So here when nickel L is being formed, it would go like this way, nickel AR. So ligand actually direct. So if my ligand is such a way that it is directing the nickel towards the above the plane position, it will always give you a stereo configuration that way, and therefore only one enantiomer selected product will be formed. So this ligand is very, very important, which directs the stereochemistry. Convergent nature. So with that, we are done with the basic things that we had to consider in this particular session, where the week two, all the 5 lectures have been covered, where we have covered 4 different coupling reactions named as Kumada, Negishi, Suzuki, and Stiller reaction, followed by we also started with the catalytic cyclopropionation, and we saw that how nickel catalyst is ruling over the palladium if you want to have an secondary or tertiary substrates. Why Kumada is not that much useful compared to the Suzuki or Negishi, because they are having the functional group tolerance, as well as they can do a carbonylative coupling. Even in that case, Suzuki is even more better because it can undergo you can form the aldehyde synthesis also. Uh, that's still a reaction, sorry. So, if there is any question, you please let me know if any concept that you have just missed out or something. Otherwise, you can just look into the questions, the problem session. So here, the first question says that the role of borate ion in Suzuki coupling is. So firstly, we need to see what is a Suzuki coupling. We have seen that in Suzuki coupling, we have R dash Br Y2, which is an organoborane compound. And here we use a palladium catalyst, also a base. So what really happens is, if I am having, say for example, R dash BY2, and if I'm using a nucleophile, it attacks onto boron, it forms R dash B nucleophile Y2. Now this becomes highly uh, carbon, this is a carbon ion, the charge is negative over here now, and this really helps in the transmetallation step that becomes faster. So to impart stability to the oxidative rotation, no, this doesn't have any role into that. To deaccelerate the palladium 2 reduction step, no. To act as a carbon ion transfer agent, that means the role of the base and this borate ion is, we are talking about the borate ion, which is only being formed when the base is involved, and this helps in the carbon ion transfer agent. It does not act as a co-catalyst because it gets consumed. So the option C is the right option. Now, this is the question for you. If anybody can answer, it would be great. This is a mechanistic cycle which is being used for mostly all the coupling reactions. So you need to define all the steps in the given cycle and predict the name of the coupling reaction. So let's see. The first one is the L2 palladium 0. We have There are two ligands, which can be anything, and it is already an active species. Now, when we are being given over here R double double dash X, that means this is a halide reagent. And if you see the process, it is forming X and R double dash L and L. So this is acting in a trans fashion. Now, this is basically when your palladium 0 is going to palladium 2. This first step is definitely your oxidative addition step. So this is oxidative addition step. Now, when you have, when you are involving R dash MgX, this is your Grignard reagent. This is your Kumada reaction basically because your magnesium has been involved. Now it will undergo a transmetallation to give you XMgX. So this is your transmetallation reaction and it would end up forming palladium R double dash L and L. Now, for doing the reductive elimination, firstly, this R and R dash has to be in a cis form. So it will actually undergo trans to cis transformation and therefore it would form L palladium L R dash R double dash and then it would undergo reductive elimination to give you R R dash. So basically, the first step is your oxidative addition. The second step is the transmetallation. The third step is the trans-cis isomerization, and fourth step is the reductive elimination. And since it is involving the magnesium, so this is a Kumada coupling reaction. I hope this is clear. These kind of questions can be asked in your exam, so please be very careful. So this is an interesting question where we are being asked to find out the major products A and B in the following sequence. So first that we will see. Please take your time to solve the question. Meanwhile, I'll just draw the mechanism over here. So you have an alkyne system and it is first being treated with a boronic acid. I will make it other way down. Right? So we will first look into this one. So this is the catechol system, which is attached with the boron system. Now this undergoes a hydroboration, meaning the H will transfer to the one carbon and the other carbon will be attached with the boron. So this will attack here. So this is called hydroboration, forming N-butyl boron, and this will be like this way, right? After that, it has been given that it has to be treated with water, and this will undergo forming a OH will attack onto your boron system, forming boric acid and giving you a catechol OH and OH. So this is your product A, which you can see out of all these things, third and fourth option can be the correct one because it is going to retain its symmetry. So it will form a E isomer followed by, if you'll see that it has to undergo reaction, coupling reaction where it will connect with your bromide, aryl bromide, alkenyl bromide in presence of the palladium catalyst. And what it would form, it has to form like bond with this one. There are three carbons, so 1 and 2 and 3. And it will then again maintain its symmetry, forming a option 4. So option 4 is correct, which it will give you this product. So I hope this is clear. Now the following reaction is aryl B boron catechol, methyl and Ar2 iodide. Now if you see the geometry, it is having a one stereo center, which is nothing but we just said that it is option A, which is a stereo convergent. Now find the suitable A in the given reaction. This is also a reaction where we have already seen that which one can give you an aldehyde. Firstly, if we are using a silly reaction or this borane can't be used because it is this can be used, but it is not that active over here. We need a base. So boron centers are crossed over here. Firstly, this is not applicable because this does not give you hydride. Even if this is applicable, we need a base to activate it. So this is not going to work. Only that Stille reaction where the tin is involved that can work. Now, if you'll see that we have a hydride over here where the CO will insert. So the A has to be HSN butyl 3. So this is the aldehyde formation using the Stille reaction. And the last question that we have is, you have been given a reaction where the alkyl halide and organoborane compound has been given. Now you need to find out which of the following statements are correct. So is this a sp3-sp3 bond formation? Yes, it is indeed an sp3-sp3 bond formation. So this one. So this is an sp3-sp3. So option A is correct. If ligand is PME3, then the reaction is feasible. We have already seen that if it is having a beta hydride elimination possibility, and if you're using a ligand which is not bulky enough, so it will not undergo the reaction. No, this is not feasible. Otherwise, if it is PCY3, that means a bulky cyclohexyl group which is attached to the phosphorus, then it can work. It undergoes beta hydride elimination if PM3 is used. So yes, the option D is also correct. So option A, C, and D, all three are correct. So with that, our problem session, and the whole week two lectures have been covered. Uh, Please feel free to ask question or any doubt that you have in hand.